this last video of content for rotation, we're going to talk about gravity. So we had learned that just gravity on Earth is equal to 9.8. Okay, well, where did they get that? In the previous videos, I explained how they came up with that, and it's using the gravitational force formula. So the gravitational force formula is capital G, which is a constant, times the mass of one object, the mass of the second object, over the radius, the distance between the two squared. So just any two objects are attracted to each other. Now, we don't completely understand this phenomenon, but you can see the reason that the Earth has such a large gravity and keeps us on our feet on the Earth is because its mass of the Earth is so large. So I'm going to give you just some constants. Well, first off, the gravitational force constant is 6.67 times 10 to the negative 11 meters cubed over kilograms times seconds squared. Okay, and then a lot of times we are looking at things that are rotating around the Earth or attracted to the Earth, so we need to know what the mass of the Earth is. So the mass of the Earth is 5.97972 times 10 to the 24th kilograms. And then the mass of the sun, if we're talking about planets orbiting the sun, we need to know its mass, which is 1.989 times 10 to the 30th kilograms. And then a lot of times we're looking at the radius of the Earth, things that are resting on the Earth. So the radius of the Earth is 6.3781 times 10 to the third meters. Actually, this is 6.3781 times 10 to the 6th. My mistake. Meters. So, if I look at this, we have two people sitting in physics class. There's a force of attraction between the two that is bringing them towards each other. If one student has a mass of 50 kilograms and the other is 60, how far apart? So we're just going to end up using this formula right here to punch in our numbers. Okay, so we have the force between the two equaling 3.20 times 10 to the negative 8th newtons, and that is equal to the gravitational constant 6.67 times 10 to the negative 11 times 50 times 60, and then divided by r squared, and we need to solve for r. So I'll end up typing this into my calculator and taking the square root, so 6.67 times 10 to the negative 11 times 50 times 60 divided by 3.2 to the negative 8th, and then I take the square root, and I end up with a distance between the two students of 2.5 .50 meters. So that's just using the gravitational constant and the force of gravity that we can apply anywhere, not just on Earth, but anywhere. We could use it on the moon, anything. So that ties into satellites and how do things have orbit. Well, if you watched the video or read the book, these objects are actually in free fall, but since there's this gravitational force towards the center of the Earth, or whatever they're orbiting, it keeps them moving in a tangential line. And so, because we learned that centripetal force is equal to mv squared over r. And this is the only force that is pointing towards, this is just whatever force is pointing towards the center of its orbit. And so gravity is also keeping it into free fall, causing it to fall towards the center of whatever it's orbiting. So we know that's G, and then M, and this is typically the mass of Earth, this first M right here, typically the mass of Earth, times the mass of the object, so in this case the satellite, over r squared. So, because remember, centripetal force is not a new force, it's just whatever forces are pointing to the center of the rotation. So I can actually simplify this formula down. The mass of the satellite in this case doesn't matter. And then we have the distance between them. One of those cancel out. And so we're left with v squared equals, and that, remember, this is tangential speed or linear speed, okay? Squared equals gravitational constant times the mass of the larger object. Typically in this case it's going to be the mass of Earth, and then the distance between the center of the rotation and the object. So I can just plug my information in for this first one and find my tangential speed. Orbital speed is what they are looking for. So gravitational constant, 6.67 times 10 to the negative 11. And then we have the mass of the Earth being 5.972 times 10 to the 24th kilograms, divided by, now this is a little bit tricky because this satellite is 1.44 times 10 to the 8th meters above the Earth. Well, and remember, this R is from the axis of rotation to the object. So we're going to need to add the radius of the Earth plus this height above it. So we end up with 6.3781 times 10 to the 6th meters plus 1.44 times 10 to the 8th meters. And then we're going to take the square root of that entire thing. So when I plug that all in, I get V equals 1,660, because we can only have 3 sig figs meters per second. So it's really cruising to prevent it from crashing into the Earth. So then the second question is, what is the period? Remember, period is how long it takes to do a complete orbit of the Earth. Okay, well, in our very first, one of our first videos, we learned about how period was related to the tangential speed. So I'm going to erase this stuff so that we can have a little more space and use that number to figure out the time it takes to make one complete rotation. Now remember, this is tangential speed that we've solved for, and tangential speed is like taking the circumference of the circle, cutting it and imagining it was on the string, and then measuring it just like it was laid out flat. So keeping that in mind, we know that the formula for circumference is 2 pi r and then divided by t, okay? And this t is the period. This is how long it'll take for it to travel the entire circumference of the orbit. So we are going to plug in our information to pi, and then we have 6.3781 times 10 to the 6th plus 1.44 times 10 to the 8th. And then we want to divide that by the 1,660 meters per second, and that will give us t. Okay. All right, and when I punch that in, I end up with 56800 seconds.